let's get started. Today we're going to be talking about a number of topics, starting with a simple introduction to Bose-Einstein condensation, and then I'll give you an overview of the theory of superconductivity. I'll just point out the components of it without actually deriving anything for you. And then we'll look at the theory of a dilute boson gas and introduce some approximations that we will use. And the theory of a dilute boson gas, and then combined with the concept that you have already seen of the probability current, will give us a macroscopic interpretation of this current quantity. And then we talk about Josephson junctions, which is the focus of today, and also magnetic flux quantization, the Aharonov-Bohm effect, and the superconducting quantum interference device, which is abbreviated as a SQUID. Okay, so let's start with Bose-Einstein condensation. So roughly speaking, in words, the concept, the phenomena of Bose-Einstein condensation can be summarized as a system of many bosons exhibit a macroscopic occupation of the ground state at low enough temperatures. So how low is low enough temperature? So low enough. Okay, so how low exactly? Now let's find out. Let's first think about this in terms of quantum mechanics. Let's think about a bunch of bosons being confined to a volume of L cubed. Okay, maybe L cubed could be 1 cubic centimeter or something. We know that if we use hard wall boundary condition, basically if we think about this as a particle in a box problem, we know that the energy levels, the ground state energy level, okay, is going to be given by k squared, and because we're in 3D, this k is labeled by a triplet of numbers, right? And for the ground state, we have this triplet of numbers being 1, 1, and 1. Okay? And then h bar squared over 2m, correct? And so now we know that there's a factor of 2 pi in the k, so let me give that to the h bar. And so this turns out to be the ground state of a particle in a box problem is 3h squared divided by 2ml squared. Okay. So I've given the 2 pi from the k to the h bar, right? And then I've factored out the l squared to the denominator. Okay. So this is for ground state, which is 1, 1, 1. Right? So for the first excited state, we know that one of them is going to be 2. So the sum of their squares is going to give you 6 here actually. So we have first excited state is equal to, okay. So with this simple calculation, we see that the energy separation between the ground and the first excited state is given by roughly 1.5 times h squared over ml squared. Okay. So now if we plug in some numbers and we find out, well, if we think about thermal excitation, now when kBT, which we will write as tau, right, is less than delta E, right, it says that the thermal energy, which is an energy you get for free being in an environment of temperature T, the thermal energy is not enough to excite a particle from the ground state to the first excited state in this temperature range, right? So we know that every particle will probably be frozen into the ground state. And then let's find out what is this temperature. So basically we just divide the delta E by KB, right? So if you remember, KB is 1.38 times 10 to the minus 24. 23, yeah, 23 I guess. And what is the unit? Joules per Kelvin. Okay. Because
can you explain why the first excited state is 6?
6, because this would be 2, 1, 1, 1, for instance, and the square root of 4 plus 1 plus 1, square root of 6, right? So when you square it, it gives you 6. Alright, so and if we plug in the numbers, we find that, and I'm using the mass of 2 electrons. And I use the mass of 2 electrons for reasons we will explain later. This is called a Hoover pair. Okay. So for the mass of 2 electrons, we find that, well, in order for them to be all locked in the ground state, we need the temperature to be approximately at 0.28 nanokelvin. Okay. So this is an extremely low temperature for you to freeze everything in the ground state by virtue of having the thermal energy less than the energy spacing between the first excited state and the ground state. Okay. So intuitively, so by thinking just about quantum mechanics, which gives energy quantization, okay, and then thinking about thermal excitation, we expect that Bose-Einstein condensation will happen. I mean, a macroscopic occupation of the ground state will happen at very, very low temperatures. Okay. So let's think about what happens at 1K based on this picture. Okay. So at 1 Kelvin, what happens? All right. So now, if we are thinking about thermal excitation, we can use the Boltzmann factor. Right? So the Boltzmann factor tells you that the relative probability of occupation is given by, so let me write P first excited divided by P ground. Right. Using the Boltzmann factor, we get that this is exponential of minus L2 divided by T. Right. So numerically, if we were to calculate this, we just plug this number, we just exponentiate this number, which is just 1, because it's such a small number. This is almost 0, so this is approximately 1. So it tells you that at 1 Kelvin, based on the prediction of Boltzmann statistics, it tells you that the ground state and the first excited state will be almost equally occupied. And that is because at 1 Kelvin, you have kBT is much larger than delta T. Right? So because the particle is free to get an energy of kBT, it doesn't really see the difference between being in the ground and the first excited state. Okay, so this is the prediction of quantum mechanics. So let's now talk about the prediction of quantum statistics. And we know that for bosons, the correct statistics to use is the Bose-Einstein statistics. Okay, so the Bose-Einstein distribution function for the energy epsilon at temperature tau is given by 1 over the exponential of epsilon minus something called mu, which is called the chemical potential, and I'll explain that later. Okay, this is given by this. All right. So if you recall, in the previous lecture, we talked about the Planck distribution, right? So what was the Planck's distribution? It was, in terms of the occupation probability, it was 1 over e to the h bar omega over k dt minus 1. So this is for Planck. And this is talking about the occupation probability for photons. Right? So we see that for bosons and photons, the only difference is this mu factor. Right? So this mu factor actually has to do with the conservation of the number of photons. Right? Because the number of bosons. Right? So for photons can be absorbed or created freely. Right? So there's no requirement to conserve the number of photons within the volume. But for a material boson, we want to conserve it in a given volume. So you need to introduce this mu factor. And I'll show you how we can conserve the number of photons. We basically relate the mu factor to the number, to the total number of bosons that we want to keep as a constant. Okay. So our previous discussion tells us that in the limit of 0 temperature, so limit as tau goes to 0, right? the ground state occupation, right, which is f of 0, now this should go to the total number of particles. Right? When I take the temperature going to the 0 limit, every particle should be frozen in the ground state. Now, this is not quite 0 yet, so if we take the limit, it should go to n. All right. So now, let's try to. This is equal to what? 1 over e to the minus mu over L minus 1. Now let me propose that actually the chemical potential approaches 0 much faster than temperature does. Okay. So that will justify us to evaluate this as a small quantity, which you can take this to be 1 minus mu divided by tau, right? And then this is approximately minus tau divided by mu, correct? And we're saying that this is n in the low temperature limit. So we see that the chemical potential is actually equal to minus tau divided by n. So first of all, you see that for the boson, for many boson system, to conserve the number of particles, it only makes sense that the chemical potential is a negative quantity. Right? So let me plot out. So we have this. And let's think about the scale of the number of particles. We say this is on the scale of 10 to the 22, 10 to the 23 per cubic centimeter. Right? So we were right to say that as tau goes to 0, mu actually goes to 0 much faster than tau, because this is to conserve the number of particles. In this limit, we need mu to be tau divided by n. Okay. And then it's an extremely large number. So let's plot the Bose-Einstein statistics. And so I'm going to put mu at this vertical axis here. And since mu is less than 0, we know that 0 is here. Okay. And this is extremely exaggerated. This should be a very, very small number. This should be a very, very small separation. All right, so this is the Bose-Einstein statistics. And this axis is your energy, okay, at some temperature. Okay. So now what is the prediction of Bose-Einstein statistics? Let's plug in the numbers we used. Right? So for the, at 1 Kelvin, for the occupation of the first excited state, assuming that total number is equal to 10 to the 22 per cubic centimeter, okay? And at 1 Kelvin, what is the probability of the first excited state? All right, so again, for the numbers that we're using, okay, we find that the occupation of the first excited state is given by approximately 3.8 times 10 to the 9. Okay. So there are, out of the 10 to the 22 particles in the box, okay, we only have 3.8 times 10 to the 9 being in the first excited state. And this is even smaller than the, and for higher excited states, the number is even smaller. So if we take this much away from 10 to the 22, we get the rest being in the ground state. So the ground state is, for the precision that we care, the ground state occupation is almost the total number of particles. And this is at 1 Kelvin, as predicted by this kind of statistics. And so even at 1 Kelvin, we already have a macroscopic occupation of the ground state. And this is by considering quantum statistics, instead of just considering quantum mechanics. Right? So actually the temperature requirement that we deduced here was too stringent. And Bose-Einstein condensation happened by a purely statistical effect. Right? Because once we consider the quantum statistics, we get that at 1 Kelvin, Bose-Einstein condensation is already occurring. Right? So this is a statistical effect. Now, what is the meaning of this is a statistical effect? So in the previous lecture, we said that quantum statistics becomes important at what range? When does it become important? we set up a calculation, but we didn't have time to finish it. We were trying to calculate the effective repulsion or attraction between two boson or Fermi particles, right? And that depended on the two wave functions to have significant overlap. So when the wave functions significantly overlap, quantum statistical effects become important. And let's see how. Let's see if we can get this out of our model. Okay? And in fact, we can. So to really calculate Bose-Einstein condensation, we need to think about what is the total occupation number of the excited states. So it is possible by doing a not so trivial integral to calculate the total number of particles in all of the excited states at temperature tau. And this tau is the temperature measured in energy. And it turns out to be, I cannot remember the formula. So and it turns out to be 1.306 V divided by 4 times 2 mL divided by H bar squared. So that the way you would calculate this is actually not that difficult. So we have the statistics function here. You need to multiply this, and you're still thinking about particle in the box. You multiply this by the density of states. And then you do an integral over all of the excited states. That integral converges, actually. That's called a Bose integral. You can do some approximations, and it converges. It converges to a factor, basically, it gives you this factor. Okay? And now, can we make sense of this? Yes. If you remember, in the previous lecture, we defined something called the quantum concentration. Okay? And the quantum concentration is this. Quantum concentration is 2 pi h bar squared divided by 2/3 power. Okay? There might be factors of 2 pi or 3 or something different from the previous lecture. And that's because in the previous lecture, we said the meaning of the quantum concentration is when the wave functions, they touch, when the particles touch each other. Right? So in the previous lecture, we treated them as cubes. Right? So depending on what you use, you could treat them as spheres. You could treat them as what is that called? Hexagons?
Hexagon or what?
But it's a 3D version of it. I forgot what it's called. But depending on the kind of geometry you use, there might be factors of 2 pi different spheres. But the order of magnitude is controlled by M, temperature, and H bar squared. Okay. So this is the important part. Forget about this if it disagrees with our previous lecture. All right. So now if we plug in the quantum concentration, what we find is that the number of excited particles in all of the excited states divided by the total number of particles is given by 2.612 times the quantum concentration divided by the actual concentration of the particles. All right, so first of all, you need to make a constraint on this. This thing is larger than 1. Right? So if the particle's concentration was equal to the quantum concentration, then this doesn't make sense. Right? Then you would have the total number of particles in the excited states being more than the total number of particles. And so that doesn't consider particles. And the reason is we are implicitly, in doing the integral, we're already working in a regime where n is actually bigger than the quantum concentration. So we're working in a regime where quantum statistics is already important. Okay? And of course that should make sense. Right? Now, what does this say? As the concentration of the particles greatly exceeds the quantum concentration by a factor of 3, we get this being appreciably different from 1. So we get a macroscopic occupation of the ground state. Maybe in your homework you can do this integral. In your homework sometime you can do this integral. Okay. So, what this means is, think about this, as the particles get closer and closer, quantum statistical effects becomes more apparent, and that's because they're more aware of each other. if they're really spaced far apart, and their wave function has very little overlap, they don't know whether they're bosons or fermions. One particle cannot know whether it's a fermion or a boson. Okay? So when there's sufficient overlap, then you have a quantum statistical effect. Okay, so now, if we want to think about, well, let's define a temperature called the condensation temperature. And this is a temperature at which the number of particles in the excited state divided by the total number of particles is approximately 1. So this is actually the regime by which this equation becomes valid. Okay, so, and you can say that see that this is just, that tells us that the concentration of the particles is basically just NQ divided by this, NQ times this. Okay. So we define that temperature, and then we can evaluate that temperature, and it evaluates to this being approximately equal to 2 pi h1 squared over n divided by 2.67. Below this temperature, by virtue of this equation, you see that the excited state divided by the total number of particles appreciably differs from 1. Now, if we plug in some numbers, and it doesn't make sense actually at this point to think about, again, the Cooper pair problem. Okay, if we plug in m to be the mass of 2 electrons here, and then we plug in n to be 10 to the 22 per cubic centimeter, which is quite a reasonable number for metals like aluminum or so, then you get a temperature that's equal to several thousand degrees, which tells you that if the Cooper pairs existed at thousands of degrees, you would already have a boson condensate, which doesn't make any sense because of two things. First of all, for that to happen, right, we cannot just plug in the 2 electron mass here. We need 2 electrons to actually behave as a boson, and we haven't talked about the mechanism for that. And in fact, that requires a much lower temperature than this does. So we are guaranteed that so long as the 2 electrons, by some kind of a correlation, behave as a boson, then we're guaranteed a boson-einstein condensate. So it gives you faith in that. And another thing is, you can think about this qualitatively. If the particle is really light, it's spread out at a given temperature. Remember we talked about thermal wavelengths. If the particle is really light, it's spread out. So it's more aware of its surrounding particle. So it requires, because we said that the overlap of the wave function basically determines these quantum statistical effects. So if a really light for a really light particle, you need maybe a high temperature. It's enough. A pretty high temperature is enough for the ECE to occur. So let's plug in some reasonable numbers, some real bosons, and then compare to whether we have some experiments. Okay. So for liquid helium, for helium-4, what is helium-4 is two protons and 2 neutrons plus 2 electrons. And this is roughly 8,000 times the mass of the electron. So 4,000 times the Cooper pair mass. And I said that this evaluates to several thousands of degrees for the Cooper pair. And for this one, it's quite reasonable. For the helium, the condensation temperature is about 3 Kelvin. Okay. And we can compare this with the experiment because we have found helium to go into a so-called superfluid state at the temperature is 2.17 Kelvin. Okay, so they are rather close. And for such a simple model, they're pretty close. Okay. So we're not just imagining things here. Things actually happen. And the modern understanding of superfluidity is just that the helium atoms form some kind of boson-einstein condensate. Okay. And then there are other forms of boson-einstein condensation and superfluidity. It can also exist in alkali gases, dilute alkali ion gases, and those mass are heavier, way heavier than this. and you get temperatures in the millikelvin, or sometimes people cool things down to the nanokelvin, and they have a very good boson and condensate there. That is the field of both atoms. So we're not going to talk about that. So this gives you a brief introduction of bosons and condensation. And it tells you what is a low enough temperature, right? So actually it's not not quite low. So it's the condensation temperature is given by this. So now I have alluded to treating two electrons which by themselves are fermions as a composite boson. Let's see why we can do that. And this has to do with the theory of superconductivity. Right? So
I mean, why don't you summarize what you said before? Because there are a lot of hand-waving arguments, and
all right.
I think it would be good for you to summarize the arguments.
Okay, so let's summarize this section. So we started by thinking about just quantum mechanics. Quantum mechanics gives us what? Discrete energy levels, right? So, and then we think about how will the discrete energy levels be thermally excited. And we found the temperature in which thermal energy is not enough to excite particles even to the first excited state. And we say that, well, certainly you're going to have a macroscopic occupation of the ground state at this temperature. Right? And we found this to be extremely low temperature.
So when you do this argument, you basically assuming Boltzmann law, right? In the background, it's the same thing.
Yes.
Well, so when you mentioned that, how does that last inequality come from? It comes from Boltzmann's law.
So we're thinking about Boltzmann. So what we mean is, although we're thinking about quantum mechanics, we're not distinguishing that the particles are indistinguishable boson. Right? We're only thinking about them as quantum particles, but we're not thinking about their statistical behavior. So now let's incorporate their statistical behavior, and we find that even at 1 Kelvin, which is 10 to the 9 times that temperature we found, we already have, roughly speaking, a macroscopic occupation of the ground state. Right? So this condensation thing is already happening at 1 Kelvin, and it's happening quite significantly too. Right? So we conclude that the Bose-Einstein condensation is a statistical effect. Okay? So this is this part. And then I tell you that if we were to evaluate the total number of particles in all of the excited states, we can arrive at this relation as a function of temperature, how many particles are in all the excited states. And then we can define a temperature at which this quantum statistical effect becomes important, which is this condensation temperature. And once the statistical effect becomes important, you will have condensation in the ground state. And that is governed by the peculiarities of the Bose-Einstein statistics. Right? And we find a condensation temperature given by this. For heliums, our simple model predicts 3 Kelvin, and the experiment tells us that something happens at 2.17 Kelvin. So it's pretty close. Yeah. So now let's move on to talk about why we can treat 2 Fermi particles as a boson. So if two fermions, for all of their interactions, if they occur in pairs, then a pair of fermions makes a boson. So let's talk about the mechanism by which this pair forms. And that is so that's a brief overview. We have only afford an overview over here of superconductivity. So maybe we can talk about superconductivity towards the end of the course, after the
Okay.
Yeah.
If we have time.
Yeah, maybe. It's very interesting. And so does anybody know when this was discovered? No, that was, he explained it. This was discovered over 100 years ago. Yeah. It was first discovered in Mercury, maybe 1917.
1913, I don't remember.
Yeah, so it's almost 100 years. Yeah, so either 1911 or 1913, I don't remember, but the discoverer is called Kimberley Owens. And he also discovered, to some extent, superfluidity in helium. Okay, So the theory of superconductivity. The phenomenon is this: when you lower the temperature, okay, the classical, semi-classical theory of metals predict that as the temperature is lowered, okay, the resistance falls off linearly as the temperature. So this is the temperature. At extremely low temperature, we get something like this. This is a classical theory prediction. But when people actually were able to cool down to temperatures in this range, which is in the several Kelvin range, and that's when they could liquefy helium. They could do this. Okay, this is resistance, maybe per unit length. And they found that, well, for a wire of metal such as aluminum or mercury, there is a certain temperature at which the resistance actually falls off like this. Okay, and this is, we call this, again, this is a critical temperature, which is for the superconductivity. This is for Bose-Einstein condensation, not the same thing. Okay. So, and people were intrigued by this. Why is there such a sudden turn off here? So let me tell you briefly why there is such an effect. Okay, so first of all, we were talking about how we can combine two Fermi particles into a Bose particle. Well, that requires two electrons to be correlated to each other. But how can two electrons be correlated to each other? We know that based on Coulomb electrostatic kind of thinking, we know that two electrons will repel each other, right, because of their Coulomb interaction. But actually, inside of a solid, the electrons don't really repel each other at long range. And the reason is that a solid is really a background. The background lattice of solids are positively charged ions. You know this from your semiconductor knowledge. Now, what happens when we place an electron in here? So there's an electron here. So the charge of the electron is going to be screened by the background ions, right? So we can have some radius, okay, above which or beyond which we no longer see the charge of the electron due to the screening effect. And this is known as the bi length. Okay. So although two electrons in vacuum certainly wouldn't be correlated because of their repulsion, inside of a metal or inside of a solid, they actually don't repel each other at long range. And the Coulomb interaction is very short range because of the screening effect. Okay. But there is a long range interaction if we think about the lattice not being a rigid thing. What happens is an electron, as it moves across the lattice, it can displace the lattice, exciting phonons. And then later, another electron comes by with some special conditions that have to be met. They can actually feel that phonon vibration and get attracted to the electron. So that is you probably won't get anything out of that, what I just said. So let me give you an analogy. Okay. So what we are saying is that if we don't think of the lattice as being rigid, we allow electrons to displace the lattice, then there is a long-range interaction. Let me give you the analogy of an elastic sheet. Okay. So we have an elastic sheet. Okay. And now I put this is elastic, and the sheet may be massive. Okay. But now I put a massive particle on it. What's going to happen to the sheet? If the particle is slowly moving, it's going to displace the sheet. Like this, right? Okay. The particle is here, it displaces the sheet. What are these wrinkles? These wrinkles are displacement of the lattice, right? Or the sheet, the elastic sheet. And these wrinkles are long range. Okay. So if we now have two particles, there's a particle here that also displaces the sheet. Okay. Hopefully I'm drawing a understandable picture here. Now the long range interaction is carried by these wrinkles. And what's going to happen is they want to attract each other. so that happens for the two massive particles on an elastic sheet. Okay. And just believe me for now, it also happens for two electrons inside of a lattice, but the two electrons have to meet very specific conditions. And the actual problem of this is called the Froelich interaction. Okay, if we were to study this, it would take about a whole lecture to do it. But maybe towards the end of the course you can do it. Okay, so all we need to do is really think about the coupling between electrons and photons at low temperature. So inside of a solid, there exists a Froelich interaction at low temperatures. Okay. So now there's another problem which is called Cooper pairing. Okay. And Cooper pairing says that provided that there's some kind of an attraction between two electrons, there's an attractive interaction between two electrons, then the electrons above the Fermi sea or close to the Fermi sea are going to form pairs. Okay, so remember the Fermi sea looks like a sphere. It looks like a sphere. Okay, so these are the kx, ky, and kz. This is the really simple picture of a Fermi sea inside of a planet. Okay, and what happens is at very low temperatures, you're going to fill in the electrons so that you fill this sphere first, and then whatever appears on top of the sphere. And because of that low temperature, there's going to be some excitation out of the from within the Fermi sea to above the Fermi surface.